So for experiment 4, what we will be doing is measuring the refractory period of the contraction of the contractile cells in the heart. And what we'll be doing to measure this is we'll put an electrode in the ventricles that we can then use to stimulate the ventricles. And what this will do is simulate a preventricular contraction. And what we will try to do is take a look at the timing of the ECG wave as we continue to stimulate and identify what the refractory period is and what the result is if we stimulate inside or outside of that refractory period. So if we take a closer look at this, what we're doing is you'll notice the action potential of cardiac cells looks something like this, where it has this long plateau phase. And the contraction of those cells overlaps that refractory period. And remember, the refractory period for a muscle cell is the point at which it cannot receive new stimulus, or it cannot contract again if new stimulus are provided. So what we're going to be doing is watching the normal ECG rhythm of the turtle heart. So if you look at this diagram down here, we notice we have this rhythmic beating, and we're going to stimulate the heart. And so the first stimulation in this data comes right here, and notice it's during the contraction of the ventricles, and because it's during that contraction period, it's also during the refractory period, and even though we stimulated, the heartbeat continues on normally. Next, what we'll be doing is attempting to stimulate somewhere outside of that refractory period, but before the next contraction in the normal rhythm. So notice that's what we've done here with this stimulation. We've timed it so that we've stimulated right after the contraction has ended, right after the refractory period has ended, but before the next contraction. And so what this represents is basically we're beating the signal from the SA node as it goes through the AV node and into the ventricles. And so we're creating an ectopic source on the ventricles, which should then depolarize the ventricles before the signal coming from the SA node depolarizes the ventricles. And so what that creates is a preventricular contraction identified here, followed by a compensatory pause. And this compensatory pause occurs because the normal rhythm of the SA node was not affected by our ventricular stimulation, and it continues on, but it lands during the refractory period of this contraction, causing a gap in the subsequent depolarizations or the subsequent rhythm of the heart. And we call that gap a compensatory pause. So moving on to experiment 5, what we're going to be doing is measuring the effect of changing the frequency of stimulus on the heart. So we won't be changing the setup from experiment 4 at all, except instead of creating a single stimulus, we will be generating a frequency of stimuli, and we will attempt to move those stimuli closer and closer together to see how they affect the contraction of the heart. So what we will be doing is we will take our heart and we will have an electrode in the ventricle, and we will be setting a rhythm or a new pacemaker. And what we should notice if we look at the force of that is as we increase the frequency of stimulations, we should notice that the force of contractions, pardon my drawing, this is the frequency of stimulations here. And if we increase that, we should see the force to continue to go down. And if we increase it too much, so if we have these very rapid stimulations, then we can actually trigger the heart to go into fibrillation, and we should see that on the ECG. So if we compare that concept to skeletal muscle cells, remember, if we increase the frequency of contraction for skeletal muscle cells, sometimes we can get those to build on top of each other and increase the force because of things like TREP summation and tetany. We don't expect those things to happen in cardiac cells, and we actually expect the force to go down as we increase the frequency of stimulations. And for the final experiment, we have a couple of videos where we will watch hearts that have been removed from the body of an organism. One's a fish and one's a human. And we'll just watch those and see what happens, and then explain why that's happening physiologically. So this video right here, this is a human heart ready for transplant. It's not hooked up to any electricity, it just has blood flowing through it. Notice how it beats. And here we have a fish heart that has been removed from a fish, and notice how it continues to beat as well.